Hello, my name is Paweł Lekki. I'm COO at EXeSS Studios, and I'm here today with Bartosz Boczula and Andrzej Czajkowski to talk about how we introduced Intel's XeSS technology into the Riftbreaker and the Schmetterling engine. So we're going to briefly talk about our studio history, our engine, how it's built and how it evolved over the years. And then we're going to move to an overview of the XeSS technology, our Schmetterling engine architecture, and how this technology was integrated into our engine, how you can do it with your own tech, and the integration steps that we've taken along the way and the production problems that we've encountered and solved. EXeSS Studios has been founded in 2007, so we've got 15 years of game development history under our belt, but we've actually started as a modding group already in the year 2003. So we've been working on a lot of game engines during these years. We've been 100% independent throughout this time, and we work exclusively on our own IP and our own games. Our roots go back to the modding scene where we've worked on making maps for different games like Age of Empires 1, StarCraft, Total Annihilation, Half-Life, the Source Engine, also Quake 3, Unreal Tournament. So we were able to gather a lot of knowledge how other game engines are built, what kind of technologies are used there, how the tools in these engines work. And that has given us a very broad overview of what's useful when making a game and what other large companies use to build their games. We've used that experience and all that we've learned there to build our own engine that suits our needs and helps us create the games that we want to create. So why did we actually create our own engine? Why didn't we use Unreal or Unity or any other engine that's available out there? So if you take a look at our history and look back at the year 2007, 2008 when we started our company, commercial engines would actually cost around $250,000. Our first project that we started when founding our company was a multiplayer car combat game called Deep Rip. That stands for Die in Pain, Rest in Peace. We built that game using the Source engine. It's actually still available on Steam. You can download it for free. And it helped us learn a lot, both about the technicalities of using an AI engine as well as the commercial side of using such an engine. To put things short, we were able to build a mod that's very well playable using that tech. But back in that day, we didn't have the funds to license it. And the best thing that we've got from building that game was a foothold on Steam in 2008. That really wasn't easy. But after releasing that mod officially on Steam, we were talking directly to Valve and we asked them, hey, what about if we make our own game? Can we release it on Steam? And they were, yeah, sure, you can build games, go for it. So we weren't able to license a commercial engine, but we had a lot of skill and knowledge, and there were quite a few open source technologies available at that time. So we decided that we're going to stitch together a bunch of open source tech and our own expertise to build something to suit our first game. what we took for start was an open source renderer called Ogre 3D. Plus, we used NVIDIA's physics and OpenAL for sound, plus a few additional open source libraries. And we built a game on top of that. And our first project was Zombie Driver in 2009. We worked on that game for 9 months. It was 3 months pre-production and 6 months game development. So we were actually able to build a game with the technology for that game within 9 months in 2009. That was super fast. One of the reasons why we did that so fast was that if we didn't release the game that time, we would be broke. So we had a lot of motivation to do that. But with that motivation and the skill that we had, it was very possible. Fortunately, that game worked well. People liked that, and we were able to fund further development thanks to the game sales without any external investors, and we moved on to porting the game to other platforms. We thought that moving our tech to Xbox 360 and PlayStation 3 wasn't going to be that difficult. We thought that it's going to take us probably 6 months to a year, and we were actually quite wrong about that, because that actually took us 3 years to get there. And in 2012 and 2013 we released Zombie Driver HD, which could have actually been Zombie Driver 2. And our technology evolved, so we've put a lot of work into our engine. We've made it cross-platform, we've made it multi-threaded. We had to take advantage of multiple threads when developing a game for consoles, because otherwise there was no chance to get performance out of that. And after releasing the game on consoles, we started working on our next IP, our next game called Xmorph Defense. In the meantime, we also ported Zombie Driver to Xbox One, thanks to which we developed our DirectX 11 port of the game, a completely new renderer that was very different to our previous DirectX 9 renderer. And Xmorph Defense was a pretty big project. It took us 5 years to finish, and that was actually the birth of the Schmetterling engine. Because first, when we were working on Zombie Driver, we didn't have a name for our technology, it was just the engine for our game. But when we started Xmorph Defense, we immediately knew that we're going to reuse the technology from Zombie Driver, and we had to call that technology somehow. So our developers came up with the name Schmetterling because it sounds cool, and that was the reason why we've picked that, and that was the basis for all of our technology going forward. We had a deferred renderer, and the game was running on DirectX 11, Xbox One, PlayStation 4, later on Nintendo Switch. So our tech was evolving, and it was very multi-platform. That allowed us for a lot of interoperability. We were able to get to these platforms very quickly and launch our games quite early in the development cycle of some of these platforms, which again allowed us to maintain our independence. Our games sold well enough to fund our studio and further development. So after Xmorph Defense, we started working on our current project, the Riftbreaker, and development on that game started in 2018. And we launched the game last year in October, so the full production cycle was 3.5 years. And the Riftbreaker is a base building survival action RPG It's a mix of multiple game genres. It's a natural evolution of the games that we've been building. The camera is top down, the thing that we've been strong with, and it includes building towers, building up your base. So that's an evolution of Exmorph defense, and it also includes lots and lots of enemies, thousands of them at once, which also can run swiftly thanks to our multi-threaded engine and the fact that we've got rendering and game logic running in parallel, all of these running unrestricted from each other. So the Riftbreaker, as I mentioned, was released in October 2021 on PC, Xbox Series consoles, and the PlayStation 5. The game sold more than 400,000 copies to date. It's a huge success for our studio, and it's going to allow us to remain independent for the years to come. And we're planning to expand on our technology, the game, and the things that are coming in the future. So we were able to expand our technology set from Schmetterling 1.0 that was available in Exmorph Defense with DirectX 12 Ultimate and its features. We've added ray traced shadows, ray traced ambient occlusion, things like variable rate shading, multiple upscalers, PBR rendering, completely destructible environments, and the game is also very moddable. We have a lively modding scene. We try to support it as much as we can because we also started as modders. We respect that community a lot, and we try to release our game and technology in a state where it's easy to modify and easy to work with. And we've actually had mods created even for the demo of the Riftbreaker that was available before the game's release, which was a huge surprise for us. And it made us confident that the game that we're working on is going to be popular even if people are modding the demo alone. So as I mentioned earlier, the development of the Riftbreaker took us 3.5 years. We have a moderate sized team of 14 people, so 6 programmers, 4 artists, 3 designers, and 1 community manager. Now we're also enhanced by an additional QA engineer. So we don't have a very big team, but as you can see from the people that are in our team, we're very engineer focused. Our biggest department is the programming department, and we like building technology, we like integrating new technology, and we love working with tech companies like Intel. And we were really thrilled to work on the new things that are coming, and integrating XeSS was also a very interesting project, and we're happy to be able to show you what's come out from that cooperation. So I'm giving the microphone to our colleague Bartosz from Intel to tell you a bit more about this technology. Thank you.
In this section, we will take a closer look at XeSS. We will see where it fits in the rendering pipeline and how it can improve the performance of your game. Next, we will cover in more details all the required inputs, and finally, we will go over the basic inner workings of the library. Now let's examine how XeSS fits into the rendering pipeline. The single game frame is usually rendered in 2 parts. The first is the scene rendering, and the second is the post-processing. In the Riftbreaker, the first part begins with the velocity pass. Then we have the G buffer, which contains the usual suspects such as albedo, normals, material properties, emissive properties, subsurface scattering, and finally the depth buffer. Going further, we have the shadow map generation, followed by screen space ambient occlusion, light resolve, and finally the forward rendering. At the end of this part, you end up with a surface in a high dynamic range containing all the geometry, all the textures, and all of the lights affecting it. And this is where XeSS comes in. XeSS takes that surface and it upscales it to the target resolution. From this point on, we begin the post-processing part. In Riftbreaker, that part consists of bloom, which requires a couple of blur passes, tone mapping, distortion, and finally the user interface. Additionally, Riftbreaker supports ray tracing. You can enable ray traced shadow and ray traced ambient occlusion. Note that the ray tracing requires even more processing power on the scene rendering side without actually adding any post-processing effects. Now let's consider how XeSS can improve your game's performance. If you render your frame in the native resolution, you render the scene and then you do the post-processing, including anti-aliasing, and UI all in the same resolution. If this resolution is high, let's say like 4K, the performance cost of that would be significant. In some cases, it could be even high enough to actually diminish your experience by not hitting the comfortable frame rate. Now, XeSS allows you to render the scene in the lower resolution, upscales the image and then do the post-processing and the UI in the target resolution. The cost of XeSS is fixed as per target resolution, so the expectation is to save the significant amount of time on the scene rendering at a small fixed cost to the pipeline and then perform the frame post-processing with the same performance as native. XeSS is also an anti-aliasing technique, so you don't need your native AA pass anymore. This gain should be big enough to actually allow you to hit the comfortable performance mark without noticeable quality degradation. And just for the reference, this scheme is different than the spatial upscaling techniques that are usually put at the end of the pipeline, just before the UI. Those techniques can potentially bring you better performance, but the quality of the output is usually worse than the AI-enhanced techniques. You can also see that XeSS, even though it would work great for every game, can have better and worse cases. The better case is obviously where the scene rendering is intense, very pixel bound, and the post-processing part is not that demanding. The other way you can look at this is, what is the percentage of workload that scales with the resolution? Not every buffer does that, like for example shadow maps. They are independent of the input resolution, and therefore not affected by XeSS. Another example are workloads that are not pixel bound, but for example geometry bound instead. In those cases, changing the resolution wouldn't affect the performance as well. In general, if the percentage of workloads that scale with the resolution is high, then XeSS will bring you the bigger performance gain. And on the other hand, if your scene rendering is cheap, but you do a lot of the post-processing, the relative performance gain might not be as good as in the first case. Additionally, if your game is already fast, hitting hundreds of FPS, XeSS might not really be a good fit, because the gain from downscaling the scene rendering might not be enough to compensate the XeSS fixed cost. Now it is time to examine what is required for XeSS to do its magic. At its core, it takes the raw color surface and it produces the upscaled anti-aliased image using trained AI network. The upscaling ratio depends on the various available quality settings. The rule of thumb is the better the final quality, the smaller the scaling factor, and in turn, the bigger the performance cost. XeSS requires two resources, a color buffer and a velocity buffer. The velocity buffer should be in the target resolution, so in most cases it must be upscaled prior to XeSS. The velocity upscaling must be made with a great precision, so the high-res velocity needs to be dilated. What it means is, basically, when you are upscaling, you always must pick the pixel that is closest to the camera from the small set of the neighboring pixels. And you can determine that by sampling the raw resolution depth buffer. Now, not every engine has a high-res velocity buffer available. And that's why, for the developer's convenience, XeSS allows low-resolution velocity as its input, but then the developer would also have to provide the low-resolution depth buffer, and then XeSS will produce the dilated high-res velocity internally. Since XeSS is a temporal technique, it requires the subpixel jitter of the main camera, just like TAA. The camera jitter is necessary for a good quality, especially for the static scenes or scenes with a very little movement. It allows enough data to be accumulated over time to properly anti-alias the edges. You might notice that all the inputs are just like TAA inputs, and you are correct. That is why if you already have a TAA implemented, you are in a very good position to integrate XeSS into your engine. Now let's take a closer look at XeSS inputs. The first input resource is the color buffer. It needs to be a low resolution, either LDR or HDR. Its color values should contain the luminance levels. To get the best quality, we recommend that the color buffer should not contain any post-processing effects. We also recommend that the color buffer should not be tone mapped, since the library does its own tone mapping, followed by the inverted tone mapping internally. The image should not be anti-aliased, since this is the part of an XeSS job. It also needs to use the higher tier MIP maps, and we will cover this a little bit later. Finally, this buffer is the one that you should apply the jitter camera to. Next, we have the velocity buffer, which contains the motion vectors in screen space presented in pixels. Each pixel contains the offset of the pixel in the current frame in relation to the previous frame. Each pixel should store two channels, one for each axis, and each channel should be at least 16 bits wide for the best quality. The motion vectors should be flattened. What it means is that the pixel movement has two components, the camera movement and the object's self-movement. So flattened means that it should contain the combination of those two components. This buffer shouldn't be jittered. Velocity buffer by default is expected to be in a target resolution and dilated. Not every engine though has that buffer on hand. That is why there is an option to provide velocity in the input resolution along with the depth buffer and let the XeSS library perform the dilation. In many engines, velocity can be presented in various spaces, such as pixel space, NDC space, or viewport space, so we have to consider that. The depth buffer is optional as a supplement to the low resolution velocity. There is a lot of flexibility when it comes to the depth buffer, so it doesn't really matter if this is a regular depth buffer or inverted one, or whether or not it's in a linear space. The depth buffer from the gbuffer path should be a good start. The camera jitter is required for XeSS just as it is required for any other temporal technique. By definition, jitter is a sub-pixel offset that is applied as a shear transformation to the projection matrix. Therefore, even the scene is static, like imagine for example any photo mode, the pixel is covered well and for the temporal supersampling. The jitter is applied to the gbuffer camera only, and the velocity should be jitter-free. And the output of XeSS will also be jitter-free. Now, XeSS requires jitter offset to be in a range from -0.5 to 0.5, so the sub-pixel requirement is fulfilled. It is recommended to use the half-tone sequence since it is proven to give the best results. This is quite common along all of the game engines, so there is a good chance that you are already using it. Now let's discuss the number of samples in the half-tone sequence. In general, the more samples with a good distribution, the better the anti-aliasing quality. The top image was collected with only one sample per pixel, while the bottom was collected with 32 samples per pixel. The scene was completely static. You can see with the naked eye the difference in the anti-aliasing quality, especially when you look at the edges of the leaves. There is however a glass ceiling. At some high number of samples, the resulting image would become blurry. Now, the upscaled pixel will be bigger and therefore will cover bigger area than the pixel of the input resolution image. In order to get the better distribution and better coverage, the number of samples in the half-tone sequence has to be increased. Note that increasing the sample number will not affect the performance. The actual value is very workload dependent, but we recommend this equation as a good starting point. Note that the value depends on the scaling factor, so the bigger the scaling factor, therefore bigger the output pixel, which requires more sampling points. Another important but not so obvious parameter is the MIP bias. As a quick reminder, MIP mapping allows to sample pixel from the lower resolution MIP if the minification happens. This happens automatically on the GPU if the screen coverage to texture coverage ratio is lower than 1. Since now we upscale our scene, during the scene rendering, it will be in a lower resolution, which most probably will affect the MIP sampling. Now the output will be in a higher resolution, so this behavior will most definitely affect the output quality, and we have to compensate for that. We can do that by providing a MIP bias, which is basically an offset to the MIP index picked by the GPU. On the top image, we have recommended MIP bias for the XeSS quality setting, while at the bottom, we have no MIP bias at all. You can see the difference in quality, especially on the texture details. Without the bias, the textures are significantly more blurry. Now, MIP bias equation that we recommend look like this. This equation depends on the scaling factor. This value can vary a lot from game to game. That is why there is this alpha value in here, so you can fine-tune to fit in your game. In the Riftbreaker, we could get away with a pretty aggressive MIP bias, so our alpha was -1. To finalize this section, let's quickly have a look at XeSS inner workings. Starting from the top, the input color buffer gets upscales and tone map. The tone mapping step is required because the training dataset was actually tone mapped too. You can think of this step as an input color space normalization. This is just a trivial upscale, non-temporal, but it also unjittered the input. The resulting image is an input to the AI network stage. At the bottom left, we can see the optional step, which is a velocity upscale and dilation using the depth buffer. This upscale velocity is not, however, an input to the AI network phase, but rather to the warp stage. Warp is essentially the history reprojection, which is in fact moving history pixels from where they used to be to where they are supposed to be in the current frame. Now here comes the interesting fact. This history buffer may or may not be used by the network. This is where the real power of AI manifests itself. So in TAA, if the pixel was discarded, effectively we miss that piece of information for the anti-aliasing. The AI, however, if the pixel gets discarded for any reason, is able to reproduce that pixel based on the knowledge it got from the training. And this is where we can introduce one more optional input, the responsive history mask. This mask basically allows you to set a given pixel history weight to 0, which effectively means that for this particular pixel, no history will be sampled, and it will be calculated using only AI power. This is useful for some situations like particles, where you don't usually store motion vectors, which can produce heavy ghosting. Another example is a semi-transparent geometry. If this transparent geometry moves, you can see both the semi-transparent material as well as what is underneath it moving. But the motion vector is only stored for the semi-transparent object, which can cause blur effect. In this case, it is again better to just ignore the history and reproduce using AI power only. In the next part, Andrzej Czajkowski from EXOR Studios will take you through the Schmetterling engine architecture, which will be useful in the following part, where we will cover XeSS integration into the engine.
Hello, my name is Andrzej Czajkowski, and I am the lead graphics programmer at EXOR Studios. I would like to introduce the Schmetterling engine for you. Schmetterling engine code is mainly based on C++ language. Additionally, we have game logic scripting support based on Lua-JIT. Our game logic code is fully written in entity component system. The whole code is highly multi-threaded. We use a thread pool and the task schedulers, which we mixed with asynchronous rendering. This creates two main engine states, which are game logic state and rendering state. Our graphics pipeline is strongly configurable and data-driven. That help us with integrating any cutting-edge graphics technologies. Of course, we support multiple platforms and have a lot of internal tools that help us to bring games for our players. The Schmetterling engine architecture can be divided into three layers. The first layer is about the whole platform abstraction. Currently, we support Windows with multiple store support, Xbox One, Xbox Series, consoles, PlayStation 4, PlayStation 5, and Nintendo Switch. Our XOR abstraction layer virtualize support for various platforms, beginning from the system API, application initializations, inputs, file system, to more user-specific features like save, achievements, sign-ins, and others. A separate thing is the render system. We support the DirectX 11 and 12, and of course special Sony and Nintendo renderers. After that, we can go upper to the main engine layer. That part doesn't have to think about the platforms and can deliver all the main features that we need to create the game. So framework, entity component system, resource system, physics, rendering, and others. This helps to create the last layer of that diagram, which is the final application. Now I would like to show you how the engine is working from the performance side. We have asynchronous game logic and rendering, and the game logic is simulated at 30 Hz when the rendering is working with full GPU speed. We highly utilize the CPU. The game logic state is working, which its own step. On the other side, we have the rendering state that is trying to render already acquired graphic states from the logic state. Both of them are working on a shared thread pool, which allow us to highly utilize the CPU. And user FPS is mainly limited by rendering state performance. So if we have a CPU with multiple cores and everything goes fine, our FPS should be mostly limited by the GPU. Here we have one of the performance frames captured by Tracy profiler. As we can see in this example, we are strongly bottlenecked by the CPU. All the threads are fully used and our rendering state is fighting with the logic side for free space to work. The first 5 threads, as you can see, those are our thread pool threads. And at the bottom of the capture, you can see separate threads like rendering state and the gameplay state. The next example frame shows us a different situation. Now we are bottlenecked by the GPU. As you can see, we have here a lot of free space on the thread pool threads. They are correlated with the swap buffer moment. Modern graphics pipelines start to use ray tracing support or are using the costly post-process. That leads us to the GPU performance. Then you can see such frame as here on the screenshot. Now let's talk about how new upscaling techniques like XeSS can help us with that problem. There are a few requirements to integrate an upscaling technique. You need to have strongly configurable graphics pipeline. It will require you to switch to various presets which have various internal rendering resolutions. Motion vector are obviously a must-have. You should already have it for your temporal anti-aliasing techniques or modern denoisers. The Jitter Offset should be there for free as you used the previous techniques. The last thing is the MIP bias override support. You can implement it on your own in your shaders in the PSO state initialization. Now I would like to introduce our compositor graph and show you how to manage that and how it helps to integrate XeSS. At the beginning of everything, we have compositor graph, which is a fully data-driven structure that handles connection between nodes. It builds a dependency graph that is deterministic. As you can see, we also group the nodes into contexts that represent separate command list that we can compute on multiple threads. Now we have compositor node that defines render target, inputs and output, and multiple passes that will be executed on the render targets. I will talk about those passes later. I also want to mention about the compositor node selector, which handles config option switching. Each compositor node has its own render target. The only requirement is to have the same input and output as others. That makes our graph deterministic and then make it simple to manage. As you can see on this screenshot here, we have an anti-aliasing switch that handles turning on FXAA or TXAA support. Now we have the compositor pass. It defines separate operation over the render target. We have multiple pass definitions, beginning from render scene and render GUI that give us all instance based on their render group, render light and render shadows. Those passes manage lights. We also have simple post-process passes like full screen, quad, cube map, compute shader execution, or clear. At the end of that, we have the possibility to create custom pass. That will help us handle everything that the game needs. The compositor XeSS pass is one of those custom passes. It has its own custom C++ implementation, which just delivers the inputs and declares the output. Here is the place where the third-party software integration begins. Now I would like to pass the microphone to Bartosz to talk about the details of XeSS implementation process. Thank you very much.
In this section, we will see the XeSS integration from the practical perspective. We will look into the Schmetterling code, now that you know its architecture, and see how it implements XeSS in a real-life game. Now, bear in mind that we have been integrating a pre-released version of XeSS library, so there is a possibility that some of the implementation details might change. That is why we recommend to start integration by reading the documentation and the development guide first, and treat this presentation as a supplementary resource. XeSS library was designed to work just like any other casual render pass in the engine. It has the initialization part that is executed only once per reset, and then the execution part that is executed every frame. For the initialization, you need to provide the D3D12 device, and the output is an XeSS context structure. You need to keep and manage this context throughout the game life. During this part, you can provide the output resolution and the quality setting. Optionally, if you choose to manually allocate memory heaps for XeSS, this is where you provide pointers to those heaps. Now, the input for the execution part are the D3D12 resource pointers to the necessary textures. Of course, in DirectX 12, you need to manage those resources, which means descriptor management and the internal state barriers. If you choose to manually manage the descriptor heap, you need to provide a pointer to it during this part. In here, you also have to provide a jitter offset and an input resolution. And finally, you need to provide a D3D command list. Now, what XeSS will do, it will put a bunch of new command lists on that list, mainly dispatch compute shaders. Depending on whether or not you choose to manage your descriptor heap explicitly, it will also set its own internal heap on that list. XeSS will not close that list for execution, so you need to take care of that. Additionally, if you choose the XeSS internal heap management, you need to restore the previous pipeline state. Let's take a deeper look at the descriptor management subject. There are two options here, the explicit and the implicit heap management, looking from the engine's perspective. In the explicit approach, you have to create and manage the descriptor heap by yourself. You have to query XeSS library to discover how many descriptors it needs, and then you have to reserve them on your heap. You can do that by calling the XeSS getProperties function. Remember to take into the consideration if your rendering is double buffered. Finally, you have to add the setDescriptor heap command on your command list. The upside of this approach is that you have a better control over the resources. Additionally, you avoid calling the setDescriptor heap function in the middle of the command list, which can potentially affect the performance. The downside is that the integration can be a little bit more complicated. On the other hand, you can let XeSS manage the descriptor heap, so the implicit approach. In this case, XeSS will create its own heap and it will internally add the setDescriptor heap to the provided command list. In this case, however, we have to remember to restore the pipeline state from before XeSS execution part. In DirectX 12, we have to manage the memory explicitly, and that applies to the XeSS library as well. But just as with the descriptor heaps, you can do that explicitly or implicitly. In the explicit approach, you have to allocate the GPU memory heaps by yourself. To find out how much memory is needed, you can query the library by calling the XeSS getProperties function. XeSS requires two separate heaps, one for buffer and the other for textures. And on the other hand, you can just let XeSS library to handle all this internally, which can make the integration significantly easier. Now, this entire XeSS scheme fits perfectly into the Schmetterling Compositor rendering architecture. In order to be able to use all of the goodness from the Compositor script, we had to implement a new class that inherits from the Compositor pass class. We would have to override two functions, init and execute, and therefore enable opportunity to just plug it into the rendering pipeline in a place and with the resources as defined in the Compositor file. That was not only convenient, but allowed us to do some debugging and experimenting quite easily. From the data perspective, we need to store and manage the XeSS context. On top of that, we are also storing a pointer to the parent render context for convenience. In the initialization phase, we have to do a couple of things. First, we have to create the XeSS context. And in order to do that, we have to get ourselves a raw pointer to the D3D device. Then we have to fill the initialization params, mainly based on the output resolution. And after that part, we can adjust the value of jitter and velocity by applying scaling. The build pipeline function will compile shaders and PSOs, possibly asynchronously. The synchronization point is actually a call to the XeSS init function. So if you want, you can compile XeSS shaders way ahead of time along with the other shaders. This function allows also to cache PSOs, but you have to provide a pointer to the D3D12 pipeline library. The Riftbreaker, however, caches PSO by storing compiled blows on the hard disk, so we couldn't use that opportunity. And finally, we can simply call the XeSS init function. Here, you can see the initialization parameters we use for Riftbreaker. So basically, we set the output resolution and the quality setting. Additionally, since motion vectors are in entity space, we have to set the appropriate flag here. Now, there are some other parameters that we can set here, for example, the flags like high resolution motion vectors or inverted depth. Additionally, explicitly managed GPU memory heaps and offset are being set here. In here, we can also provide the PSO library pointer for XeSS to look up its cached pipeline states and shaders. Now let's take a look at the part that is executed every frame. In Riftbreaker, we have chosen the implicit descriptor heap management mostly for convenience. That's why we have started this function by storing pointer to sampler and texture descriptor heaps from the parent render context. Then we have a helper function that fetches input texture pointers. We do that every frame because the game is actually double buffered, meaning that underlying textures, even though it might look the same, can actually have different addresses and might require different variants. Next, we have to do a little bit of a barrier management. And finally, we can call XeSS execute function with provider pointer to the command list. We also need to restore the previous pipeline state, which in Riftbreaker is simply restoring the descriptor heaps. Note that we are not closing the command list explicitly. This is thanks to the engine's architecture, which is really convenient and allow us to possibly put our paths in any place we want within the same render context. Let's move forward to specific functions from the execute function. The first function simply fetches the resources. We use indices here, so in the compositor file, we have to put the resources in a particular order. We can also see that for the depth, there is another index in the am_texture member, and that is because this texture is a part of the gbuffer multi-render target. The second function is the internal resource state management. XeSS requires that the color, depth, and the velocity needs to be in a non-pixel shader resource state. Render context has a convenient transition resource function, which makes our integration much easier. We just mark the resources we want to manage, and everything else is being done automatically, including moving resources back to the initial state. The flush resource barrier function executes the barriers. The last requirement is that the output texture should be in unordered access state. We do this in the compositor file where we declare our output texture. And this transition is being done automatically thanks to the thoughtful engine's architecture. This is where we deliver all it's needed by XeSS. First and foremost, this is where we provide the D3D12 resource pointers to the required textures. Then we set the jitter offset with change every frame. Note that those have to be in sync with the offset that is applied during the gbuffer. You also provide the input resolution. And if you choose to explicitly manage descriptor heaps, this is where you provide the parameters to them. On top of that, you can provide the exposure scale to the correct color buffer if necessary. This buffer should be the same that you provide to the tone mapping render path, since it will also be using the internal XeSS tone mapping. Exposure simply helps to bring the input color, which can be over or underexposed, to proper exposure range. And finally, you have the possibility to reset history. That might be useful when you know that your scene changed so much that the history buffer is no longer valid and should be simply discarded. Now let's see how Schmetterling handles the jitter offset. The usual halton 2 and 3 was used, which is in line with the recommendation. One of the input parameters is the number of samples, which can change depending on the quality setting. Then you calculate the halton for both x and y axes. After that, you need to translate those numbers from 0.1 range to -1 to 1. Then you divide by screen dimension, which is basically transferring offset to the pixel space. Finally, you set the offset as a part of the projection matrix, which effectively is like applying a shear transformation. So what XeSS really requires is the corresponding Halton number, but transferred to the -0.5 to 0.5 range. Motion vectors can potentially be tricky, so let's see how Schmetterling handles them. In the velocity shader, the inputs are current vertex position, current world view matrix, and previous world view matrix. The velocity is calculated by simply calculating the screen space position from current frame and then subtracting the same vertex position in the pixel space from the previous frame. This value is in pixels. Then, this value is divided by the viewport dimensions, effectively transforming them to the NDC space. And therefore, we need to set the appropriate flag during the initialization. This algorithm is repeated for every object visible on the screen, both static and dynamic. From XeSS perspective, that means that we know for a fact that the velocity buffer is flattened. The accumulated velocity value contains both the object and the camera movement. In other engines, there might be a different approach, so keep this in mind. For everyone that has been working in software development long enough, it should be a known fact that there will be situations where something simply doesn't work. In this chapter, we will cover some of the tips when this happens and how to debug. One of the possible issues might be related to jitter. Sometimes you forget to set the offset, or offset is not in sync, or offset is in either different directions or different scale. All of those jitter-related issues usually manifest themselves by this jittering, or in other words, like shake of the camera. To make sure that this is an issue, you can, if you have that option, set the delta time to 0. If the jittering is still there, there is a huge possibility that it is related to jitter, because jitter is frame rate dependent and not game time dependent. To be even more sure, you can set your velocity scale to 0, which effectively will make each motion vector equal to 0. If this issue is still there, then for sure it's related to jitter. Another portion of potential issues might come from the motion vectors. They can have different than expected directions, they can have different values, or they can be stored in a different space than expected. So for example, in the viewport space instead of NDC space. Finally, they can actually be in the NDC space, but the NDC space flag might not be set. As opposed to the jitter, velocity is independent of the frame rate, but is dependent on the game time. They will manifest themselves during the strong geometry movement, like for example animation or from the camera movement. As an example, I presented the incorrect direction of the motion vectors. In this case, if you move the mech, there is a strong shimmering showing up due to the wrong velocity value, and in turn, wrong history reprojection. But if you don't move, there is no issue. Now let's take a look at the quality that you can actually achieve by using XeSS. So first, let's take a look at the simplest possible upscaling, which is a simple bilinear sampler, without using any anti-aliasing techniques. As you can see, the results are not satisfactory. There is a heavy aliasing and blurring visible. The next step would be the same upscaling, but this time with TXAA. The aliasing quality is vastly improved, but also there is a blurring. This image was produced using XeSS with 2x scaling setting. Both the aliasing and the blurring is gone. The image looks sharp. Remember that there are more XeSS settings, so you can sacrifice some of the performance to get even more quality. And just for the reference, this is the native rendering in 1440p, so no upscaling at all. The differences between this and XeSS are marginal. The images are almost indistinguishable. The differences are even harder to notice if you just casually play the game. Finally, here are some of the close-up for a quality comparison. And that concludes our presentation. We hope that you found it interesting and then you gathered enough knowledge to integrate XeSS in your game engine. If this is the case, then please contact me at this email so we can discuss this further. Now, just before we let you go, I just wanted to mention that this work is an effort of many people. I would like to thank everyone that helped us during this process. the entire XeSS team for the support, and the lab for testing the game for us. And here are the special thanks to the people who worked directly with me on this integration. And of course, huge thanks goes to our friends at EXOR for wonderful cooperation.